How do we use Monte Carlo simulation to solve the Newsvendor problem? Well, if you're asking that question, you've come to the right place, because in this video, we're going to have a go at coding a Monte Carlo simulation in Python that's going to tackle a simplified multi-period newsvendor problem. So imagine that you're a news vendor and you own a newsstand and you want to sell the Financial Times. At the start of each day, you purchase Q copies of the Financial Times for 30 pence each, and you sell them for 75 pence. Now, it might be that you have a bad day and you don't sell all of your copies, but all is not lost. You can recycle those copies and receive an income of 5 pence per recycled paper. You can only purchase newspapers in batches of 10, so 40 papers, 50 papers, and so on. And you've collected data over a number of months, and you've found that the number of sales you have follow 3 probability distributions, depending on if it's a good day for sales, a typical day or fair day, or indeed a poor day for sales. Each of those days has its own discrete probability density function that you've observed empirically. We'll take a look at those in a moment. These are newspapers, so you don't carry stock over from one day to another, you recycle them. So at the end of the day, there's no carryover of inventory from one day to the next. And you are interested in finding the optimal order quantity that maximizes your profit over a working month. So 5 days of the week for 4 weeks is 20 days. So you're looking at a multi-period problem where you're trying to maximize your 20-day profit. All of the code I'm going to go through in this video is available online. I'll link to that in the description below. As always, if you find any of this material useful, please smash that like button and subscribe to the channel. Before we take a look at the model in action, let's have a look at the probability distributions underpinning this problem. So the first is we have a day type probability distribution. This is a discrete distribution. So we're either going to sample that it's a good day, a fair day, or a poor day. And most of the time, 50% of the time, it's going to be a fair day where sales will be reasonable. 32% of the time, it will be a good day. And then some of the time, 18% of the time, we'll have a poor day. Once we've specified the type of day it's going to be, we can select the appropriate discrete distribution from our demand table. So we have demand ranging in tens from 40 through to 100 newspapers. And we've got 3 discrete probability distributions here. So we can pick, for example, the good day and see that there's an 8% chance of selling 100 newspapers. Whereas if it was a poor day, there's a 0% chance of selling that many. Let's take a look at the model in action. I've stored all of the code in a module called Newsvendor. What we'll do first is we will run the model and have a look at the type of data that is outputted from it. So we're going to create an experiment where we specify parameters. So the first thing we're going to do is look at an order quantity of 70 newspapers a day, that's Q, and we're going to have a planning period of 20 days. So we're going to look to maximize profit over those 20 days. Then we pass the experiment and the seed to the single run function, and that returns a simulated result. What that outputs is a pandas data frame where we have the day of simulation versus the type of day that has happened. So for example, on day 1, we sampled a fair day. From the fair distribution, we sampled 50 sales. So our sales revenue was 2,500 pence. We weren't short of any on that day, but we did have newspapers left over. We had 20 newspapers left over, so we sold those for 5 pence each. So we can then work out the cost for the period and the profit. So we stored that pandas data frame in a variable called simulated result. We can pass that to a function we've imported called period statistics and show a summary of that period. So we can see that our total profit was 15,130 pence or 151 pounds. You can see the minimum profit, the maximum profit, and some percentiles as well. So that was only one simulated run of the model. In practice, we'll want to run a lot more of that to look at the distribution of profit. So here we're going to run 10,000 replications of the model using the multiple replications function. So the first experiment we're going to create, we're going to order 80 newspapers per day, and we're going to look at profit over a 20-day period. We'll pass that experiment and the number of replications to the multiple replications function. That'll give us a pandas data frame, a replication results table, and we'll just have a peek at the head of that. So here we can see the first 5 rows of that pandas data frame. Remember, it's quite big. There's 10,000 rows in there. So for each replication of the model, we can see the total profit over the 20-day period, the minimum value, the maximum value of profit, as well as the percentiles. Now we can visualize that as a histogram using the create profit histogram function that's included in the module. So I'm just going to pass in the profit column, and as we're in pence, I'm going to divide through by 100 to convert that into pounds so it's a bit more readable. So here we have a histogram of the replication results. So lots of information on this chart. The frequency on the y-axis represents the number of replications where a given profit, shown here on the x-axis, has been returned. And we can see on average, the mean was roughly £110. And there was a 90% chance that the profit returned was between £67.80 and £151.60. We can then compare the distribution of profit that we saw from simulating an order quantity of 80 to different order quantities. For example, we could explore the profit over 20 days by ordering 70 newspapers a day. So again, we'll create a new experiment. We'll call that scenario. We'll pass that to the multiple replications function and we'll run 10,000 replications again. We'll return that as a pandas data frame called scenario rep results. And then what we'll do is we'll look at the difference between profit in our new scenario where the order quantity is 70 with our scenario where the order quantity was 80. We'll store that pandas data frame in a variable called profit difference, and then we'll plot the difference and take a look at is there a positive or negative difference between those two scenarios. So here's the histogram of difference in profit between an 80 scenario and a 70 scenario. So a positive value shows that ordering 70 newspapers is a better strategy than ordering 80 newspapers per day. So we can see on average we would expect to make £28.61 more over the 20-day period, and we would expect that 90% of the time that would fall between £6.40 and £43.60. We can see there are some instances where we don't make more profit, we actually make less profit. So it would be good to also estimate the probability of ordering 70 newspapers being a better policy than ordering 80. Here we have the cumulative frequency plot of the same data. So we can look along the x-axis and see where 0 is. And from that we can determine there's a less than 1% chance policy of ordering 70 newspapers will return less profit than a policy of ordering 80 newspapers per day. So I think that's good information to help you as a news vendor make the decision about which number of newspapers to order. Now that we've taken a look at how we use Monte Carlo simulation to solve the news vendor problem, let's take a look at how I've implemented this in Python. Now the news vendor problem comes in many different flavors. The good news is the framework that I'm going to show you here is easily adapted to your own version of the problem. The first thing I've done is I've set up a discrete distribution class. That's going to take 3 parameters. The first is an array-like object of values, so a Python list or a NumPy array, for example. A list of associated probabilities for those values will also need to be passed in. We can also optionally set a random seed. So if we needed to, we could get repeated results from this class, which is indeed how we've set up the Monte Carlo simulation. Values and the probabilities are stored internally as NumPy arrays within the class. I've also set up a NumPy random number generator, and that's going to allow us to sample from those probabilities, and optionally you can pass in the random seed to that. There's a sample method that we can call. That's going to use the NumPy random number generator, pass in the values and the probabilities, as well as an optional parameter called size that determines how many samples we return to the user. Creating an instance of the discrete distribution is really straightforward. So here I'm going to create an instance that I'm passing into a variable called dayType. I pass in my variables. So here I'm passing in values of good, fair, or poor. I'm passing in some probabilities that I've made up, and I'm passing in a random seed. Once that's created, I can call the sample method of the class and pass in a size parameter to determine how many daytypes I would like to return. As usual, we're going to manage the parameters of the model through an experiment class. The first thing I've done is declared a number of default values for an experiment. So a default number of periods that we're going to simulate, a default order quantity, we've got default purchase cost, sale price, and salvage price. I've specified links to 2 CSV files that contain the discrete distributions we're going to use in our sampling. And I've got some parameters that represent the number of random number streams we need to create, as well as a main seed that we'll use to parameterize the model. So the experiment class takes a form similar to what we've used before. We're going to pass into that the number of periods we want to simulate, the order quantity, parameters to do with the calculation of the daily profit, parameters that specify the location of those discrete distributions in CSV files, as well as our streaming instances. All of those have the default values, so if we wanted to, we could just create an instance of the experiment class and immediately run a version of the model. The initializer of the experiment class simply stores those parameters in member variables. In practice, we might want to do a bit of validation here as well to make sure that only valid parameters are passed to the class. We might do a bit of calculation. For example, the profit per unit is the sale price minus the purchase cost, and so on. We read in the CSV files that contain those discrete distributions and store those as pandas data frames within the class. And then we set up the sampling. And all of our probability distributions, which are all going to be instances of discrete, are going to be stored within a dictionary called dists. We have a method called setMainSeed. That's going to be called externally by a function that runs the model. It passes in a main seed. That main seed is going to be used to set up all of the random sampling within the model. It's going to allow us to get a repeatable run of the model. Finally, we have the initialize sampling method. That's going to create an instance of NumPy's seed sequence object. That's going to guarantee we have n non-overlapping streams. That's where the main seed goes. And then using the seed sequence, we spawn n streams and store those seeds within a member variable called seeds. So then to create instances of the distribution is simplicity itself. For the daytype, we create an instance of discrete and we pass in information from our pandas data frame to do with the daytype, and we also pass in the first seed from the list. For the demand distributions, depending on what type of day it is, we're going to do that in a loop. We're going to loop through the names of the days, so good, fair, and poor, and we're going to create instances of each of those. And so the first one, for example, will be a good day. That will have a key equal to good. We'll pass in the demand profile and we'll pass in the probabilities for the good column in the pandas data frame. and we'll pass in the second seed within the sequence. And then we'll go back round that loop and do that for fair. We'll go back round that loop again and finally repeat that for poor. So just to give you an example of that experiment class in action, here we'll create a default experiment by just creating an instance of experiment. And for example, we can see we can access the day type distribution using the dists dictionary and passing in the key day type. And if we wanted to sample from the fair distribution, we would pass in the keyword fair and call the sample method, and that would return, in this instance, a value of 40. One way to think of this Monte Carlo simulation is a way of generating tables of data. Those tables contain rows, which is a day within the 20-day planning period, and columns. So we need a method to generate each of those columns. So the first three that we're going to look at are getting the sales revenue, getting the shortage cost, and getting the salvage value. So the sales revenue function is going to return a NumPy array. So it returns a column of data within that table. We're going to pass in an instance of the experiment and a demand array. So the demand array is a column of data within that table. It contains the samples for that replication of how much demand there's been each day. So with sales, we either need to pick the minimum of the number of newspapers we've ordered or the demand. So the first thing we're going to do is create a sales array equal to the order quantity. We then look at the difference between the order quantity and the demand, and finally update sales to be the minimum of the order quantity or the demand. To turn that into revenue, we simply multiply the final column, which is the number of sales, by the sale price. You can then think of running one replication of the model as generating one table of data. So we have two functions, single run, which creates that table, and then period statistics, which simply calculates the total profit and some other statistics of interest over that 20-day period. The single run function accepts an instance of experiment and a replication number. We're going to use that replication number as the random seed within our sampling. Single run's also going to return a pandas data frame, which is our table of data. So the first thing we'll do is set the main seed of the experiment. That gives us our reproducible result. We'll then sample the day types. So if we've got a 20-day planning period, we'll return 20 string values representing whether it was a good, fair or poor day. We'll store that in a value called day types. We'll then simulate the demands on the day from the appropriate distribution. So we'll loop through that array of day types and we'll select the correct distribution from our experiment distributions dictionary, call the sample method and store that in a Python list called demands. We can then construct the columns within our table of data using those functions we've just been through. So the sales revenue column, we call the get sales revenue method. We do the same for shortage costs, and we do the same for salvage values. To calculate the cost of purchasing newspapers, we simply multiply the order quantity by the purchase cost. We're going to fill a NumPy array, and that's going to be of size 20, and we'll store that in a variable called period costs. The last bit of code within single run simply converts all of those NumPy arrays into a pandas data frame. That's really for convenience for us to view. It takes those NumPy arrays to calculate profit, which is the sales revenue minus the period costs minus the shortage costs plus the salvage value. And we return those results to the user. The period statistics function is nothing to get too excited about. We simply accept a pandas data frame or table of data. We're going to return the result as a dictionary. total profit is just the sum of the profit column, and then we call the other universal functions from the pandas data frame to calculate minimum, maximum, etc. So now we're back down to be able to run a single run of the simulation model and obtain a table of data. Let's create an instance of experiment. We'll run a order quantity of 70 and 20 periods, and we will use replication ID 1, and here's our results. So we can see that on day 1 it was a fair day and our profit was 290 pence, and on the second day it was a good day and our profit was 1020 pence. If we rerun that model, we get the same result because we've not changed the seed. In order to obtain a different result, we would change the value to 2, and we can see that our first day is now a poor day, where we have actually lost 160 pence overall. We could change the way this problem works by, for example, changing the number of periods that we're interested in. For example, we could change that to 2 periods, run the model, and we would return results for only 2 simulated days. So you should be able to see that in order to run multiple replications of this model, all we need to do is have a loop that reruns our single run function and calculates the total profit. So that's what the multiple replications function is doing. We're passing in our experiment and the number of replications we're going to run, and we return a NumPy array containing the total profit over those replications. So we have a list comprehension that simply reruns single run function nreps time. The replication number that we pass in, which remember sets the random seed and controls reproducibility, is simply a counter variable coming from this range object here that's going from 0 to 1 minus number of reps. We have a Python list of results, and we're just going to simply convert each of those to a data frame with different columns representing the different performance measures. So for example, if we wanted to run an experiment with order quantity 70 and periods 20 for 500 multiple replications, we just need to call the multiple replications function now, and that will return a pandas data frame, and we can peek at the head of that. And we can see here that we have replication numbers. We've just got the head, so we've got the first 5, and we have a column for profit, which varies depending on the day. And finally, we can then summarize those simulated profits, either using built-in functions such as the describe method of a pandas data frame, or we could go back and call the plotly function, which created histograms and cumulative frequency distributions to analyze the problem further. Monte Carlo simulation is a super flexible approach. This is applicable to many problems. The only thing that might hold you back is potentially a lack of data, or maybe just the need for a bit of inspiration. If that's the case, check out this video here, where we use Monte Carlo to explore an investment problem. Thanks for watching, and I'll see you in the next video.